Again, we said, going one step back, we said this equation can come from the equality in partial pressure at the interface. So I can say the Yj, the mole fraction of each component in the gas, is divided by mole fraction of that component in the liquid is equal to PVJ over P. So Yj becomes Xj times PVJ over P. That's one equation. I can write the material balance, okay, and I can say the mole fraction of any component in the total mixture times the total of number of moles in the mixture is equal to the mole fraction of that component in the liquid times the total number of moles in liquid plus the mole fraction of that component in the gas times the total number of moles in the gas. And then I can replace Yj or Xj with equation 12.2, and then I can come up with the equation 12.14. Then here I can factor the Xj out and have the Xj being equal to Zjn over NL plus PVJ over P times Ng. I know the N is equal to Ng plus NL. The total number of moles is number of moles in the liquid plus number of moles in the gas. I can normalize that equation, then NL bar becomes plus Ng bar becomes equal to 1. And then therefore NL bar is 1 minus Ng bar, okay, or Ng bar is equal to 1 minus NL bar. And then in this equation, so if I divide the numerator and denominator by n, so the n goes here, NL becomes NL bar, and Ng becomes Ng bar. Now instead of Ng bar, I'm going to put 1 minus NL bar, and I'm going to factor the NL bar out. So if I do that, then I will end up having equation 12.18. Depending on if I'm writing for mole fraction in liquid or mole fraction in gas, I will have equation 12.18 or 12.8 or 12.9. Okay? So for ideal solutions, if I want to find the mole fractions of the mole, if I want to find the compositions in the liquid, okay, what I would do for finding the composition in the liquid, I'm gonna use equation 12.8. In that equation, the Zj, total number of mole, the composition of a mixture should be given. So I know what components are mixed. Okay, I just don't know how much of which component went to the gas or liquid. So I know, and what's the composition of gas and liquid. So I know the composition of mixture. So this is given by question. So now that I know the composition, I can find the PVJs. For every pure component, I can find the vapor pressure using the Cox chart. The total pressure is also given. What I don't know is what's the number of moles in the gas phase, okay? So I can assume a number, calculate the summation, and see if it's equal to 1 or not. If it's equal to 1, therefore the Ng value that I picked is the right Ng value. If not, I'm gonna iterate on this till I get the right Ng value, okay? I'm gonna just make another assumption. And if you remember from our previous lecture, we said with these type of equations, we can solve it only by two assumptions, and then assuming that there is a linear interpolation valid between those. So I'm going to plot the summation versus the Ng value, and I can say for Ng, the first guess, I got the summation, let's say, greater than 1. For another Ng guess, I get the number, let's say, less than 1. And then I can linearly interpolate and say what would be the right Ng that can give me the summation being equal to 1. We'll go over an example. So if I have this, then I can find the mole fractions of the liquid, which is simply for every component is equal to the composition of that component in the total mixture divided by 1 plus Ng times PV of that component over total P minus 1. Now that I have the Xj, I can simply find the Yj because Yj was equal to Xj times PVJ over P. So if I have the mole fractions of the liquid, I can simply find the mole fraction in the gas. If I have Ng, number of moles in the gas, 1 minus that is the number of moles in the liquid. So I can find the composition, Xj and Yj, and also the quantities, Nj and NL, Ng and NL, for any pressure and temperature inside the two-phase for the ideal mixture using either equation 12.8 or 12.9. Okay? So let's do an example. So example 12.1 says calculate the composition and quantities of the gas and liquid when 1 pound mole of the following mixture is brought to the equilibrium at 150 degree Fahrenheit and 200 psi. So the temperature is given, the pressure is given, The total number of moles is given. The composition of the mixture is also given. Okay. So for this, as I said, I can use either equation 12.8 or 12.9. Okay. So 12.8 is written for the mole fraction of liquid. 12.9 is written for the mole fraction of gas. So in this example, we have used the equation 12.9. Okay. So we have using equation 12.9. So we are solving for mole fractions of the gas. So I write the equation. The ZJs are these mole fractions in the mixture. These are given. Pressure is given, 200 psi. PBJ, the temperature is given, so I can go to the Cox chart and read the PBJ, the vapor pressure for propane and butane and N-pentane. Okay, so this is I can find. So that said, I just need to know the NL. So I'm gonna guess the NL value. I assume, let's say it's 0.5. So if it's 0.5, then I can find the summation. I can calculate this ratio for every component, and then I can sum them up and see if it's equal to 1 or not. So let's do that. So here for the first guess, okay, here basically it's just going to show, it's just showing you the last iteration. So it says in order to save time, we just show the last trial. So if you were to assume the NL being 0.487, okay, so if NL assumed to be 0.487, then the components are given, the mole fraction in the mixture is given. At the 150 degree Fahrenheit, I can go and read the vapor pressure from the Cox chart. So these numbers are coming from the Cox chart. And then for every component, I can calculate this ratio. So Zj, which is given, divided by NL, which I assume 0.487, times the total pressure, which is 200, divided by PBJ minus 1. I can calculate these ratios, and then I can sum them up. If the summation is equal to 1, great. Then it means this NL value is the right NL value. Okay. Then if that's the case, then Xj simply becomes Yj times P over PBJ. Okay. Again, Yj I already calculated, P total pressure 200 given, then the PBJ I have for every component. So I can calculate the Xj. So I can have the mole fractions of each component in the gas and mole fraction of each component in the liquid. The number of moles in the liquid, I just guessed value, and that's a correct one. So it's 0.487. Number of N in the gas becomes 1 minus this. So it becomes 0.513. Okay? And since I had only 1 mole, so that's in the mixture, the total mixture. So that's the correct value. Okay? So if, again, if you go back to our previous lectures, you will see if I wanted to do this example without using this, what I would do was I could simply plot. I could simply do this. I can simply plot this and I could say, hey, I want to have in the y-axis the summation, and the x-axis, let's say in this case NL. Okay. So I'm going to guess a value. Let's say I'm assuming the first NL being 0.5. If I assume NL being 0.5, I can calculate this Yj value for NL of 0.5. If you do that, this summation becomes, let's say, greater than 1. Okay, let's say I have done that, and then the summation turns out to be so for 0.5, I've done that, and then the summation turns out to be a number greater than 1. Okay, and let's say this is the summation being equal to 1. So this is the summation being equal to 1. I guess a value of NL to be 0.5. Okay. So I guess the value of NL being 0.5. And then I get the value greater than 1. I can guess another value. Let's say I guess another value, and that's 0.7. If I assume 0.7, I can plot the 0.7 and L here and recalculate this ratio, and then I can calculate the summation. If I do that, let's say the summation turns out to be less than 1. Let's say it turns out to be 0.9. Okay? So at 0.5, my ratio is, let's say, 1.1. At 0.7, the ratio is, let's say, 0.9. What would be the correct n value that gives me the summation being equal to 1? And then for that, I can simply do the linear interpolation and say, at what condition my summation becomes equal to 1? And that's basically this one. Okay. So by two assumptions and with two readings, and assuming that the relationship is linear, I can find correct values. So let's say I assume 0.5 and I got the value greater than 1. I assume 0.7, I got the value less than 1. And then I write the equation of this line because I have 2 points on that, and would say what would be the y, what would be the x that can give me a y being equal to 1. So one equation, one unknown. So I can find the x, which is the exact NL value. So I need to have 2 trials. When I have that, then I can get the right NL. So if this is the final NL, then the summation will add up to 1 for the gas, and then I can find the summation for the liquid. So this is for the case where we have the ideal solution, and we are interested to find the quantities and composition of the gas and liquid in the mixture. Okay. How about the bubble point pressure? Remember, we were interested in 3 quantities: the bubble point pressure, the dew point pressure, and the gas and liquid composition and quantities at any point in the two-phase. So the gas and liquid composition and quantities at any point in the mixture can be obtained with the previous discussion, the previous example. Here we are going to look at the how to find the bubble point pressure. So if I write the equation again, okay, if I write this equation, I can start with the summation of Yj, the gas composition, being equal to this ratio. I can say at the bubble point pressure, basically the bubble point pressure is defined as the pressure that the first gas bubble is appearing. So practically the number of moles in the gas is equal to 0. If the number of moles in the gas is equal to 0, then the total number of moles becomes equal to NL. So N becomes equal to, NL becomes equal to N. So these two cancel out, this becomes equal to 0, where at the condition that the pressure is bubble point. So P becomes PB. Therefore, this summation will simplify to the summation of Zj divided by PB over PBj. I know the PB is a constant number, so it can come out of the summation. So PB becomes the summation of Zj times the PBj. So if I'm interested to find the bubble point pressure of the ideal solution, and if I have the mixture composition, I can simply find the vapor pressure from the Cox chart, multiply the mole fractions by the vapor pressure, and sum them up. That's my bubble point. So example 12.2 says, calculate the bubble point pressure at a temperature of 150 for the mixture given in the previous example. So in the previous example, we have the propane, N-butane, and N-pentane, and the compositions in the mixture were given. So if I'm interested to find the bubble point, what I would do is I would simply find the vapor pressures from the Cox chart. So what is the vapor pressure of propane at 150 degrees Fahrenheit? That's 250 coming from the Cox chart. What is the vapor pressure of N-butane at 150? That's 105. And the same for pentane, which is 37. I will get the PBJs. So Zj times PBJ. Zjs were given, multiplied by PBJ, and then sum them up. That becomes my bubble point pressure. Again, remember, this is the ideal solution. If this solution is ideal, then the PB, the bubble point pressure, is simply the summation of Zj times PBJs. Very, very simple.